So I'm delighted to introduce Dr. Duna Roda-Boluda, the winner of the Dick Chorley Award for outstanding work produced from PhD research. I was lucky enough to be an undergraduate student when Duna was completing her PhD at Imperial College London, so I've seen her work in action, so I'm particularly looking forward to this. The Dick Chorley Award was given to Duna based on her 2019 paper, beryllium-10 erosion rates controlled by transient response to normal faulting through incision and landsliding. This work combined field geomorphology and cosmogenic nuclide dating. The panel considered this paper to demonstrate excellence by linking a process-based understanding of landsliding with field data, geochemistry, and modelling across a wide range of temporal and spatial scales. Duna is a previous Bernie Smith Award winner and recently held a Marie Curie Fellowship and has received multiple awards for her contributions to science already, which are testament to her diverse talents and interdisciplinary approaches to geomorphology. And just last week, she started as an assistant professor at Vrije Universiteit in Amsterdam, and she will hopefully be recruiting PhD students next summer. So lots of exciting things happening for Duna. Let's hear her talk.
Hi everyone, thanks for the invitation to speak today. I'll be speaking about investigating landslide activity over millennial timescales using cosmogenic radionuclides. This is the overarching topic of two different projects that I'll be talking about. And before I start, I'd like to thank and acknowledge my co-authors. So for the first part of the talk, I'll present the paper that's received the Dick Chorley Award by the British Society for Geomorphology. Beryllium-10 erosion rates controlled by transient response to normal faulting through incision and landsliding. I would like to extend a special thank you to my colleagues on this work, and also to BSG for the award. The BSG annual general meeting was the first conference where I presented my work as a PhD student, so I feel very honored to be presenting this now as a medal recipient. And for the second part of the talk, I'll present some unpublished results of my postdoc project that I'm developing at the GFZ Potsdam with a Marie Curie Fellowship. So before starting, I would like to take a step back and remind you why are landslides so important. So landslides are the primary erosional mechanism in mountain areas. So by understanding and quantifying landslide erosion, we are already getting a very big chunk of the full picture of erosion and sediment fluxes from mountain areas. Landslides are also one of the fastest processes that turn bedrock and relief into sediment. So they connect erosional and depositional landscapes, and hence are very important for landscape evolution studies. Partly because of that, they are also very sensitive to perturbations in climate and tectonics. So landslides can potentially be a marker for these perturbations. And finally, as many of you know, landslides are one of the greater geohazards. So we are hoping that by better being able to constrain their long-term and past activity, we would be able to make better future predictions. But the problem when studying landslides is that it is extremely difficult to constrain their long-term rates of landslide activity. And by long-term, for the rest of the talk, I'm going to be referring to timescales of between hundreds to thousands of years. And that is because the physical records of landsliding, so the landslide scars and the deposits that they leave behind, are often removed in less than 100 years by further erosion. And the aerial imagery-based inventories that we can obtain now can only integrate between years to decades. So at best, they are only capturing a very short time span that may not be representative of the true long-term activity. So the overall aim of the work that I'll show you today is to quantify landslide frequency and erosion rates over hundreds to 1,000 year timescales. And the tool that I'm using to do that are cosmogenic radionuclides. So a brief overview on cosmogenic nuclides for those of you who may not be familiar with them. So these are nuclides that form in the atmosphere and top few meters of the bedrock due to the interaction of atoms with the incoming cosmic rays. So they are nuclides such as carbon-14, beryllium-10, or helium-3. They are only produced in the top few meters of the bedrock because as these cosmic rays penetrate through dense material, the production of cosmogenic nuclides decays with an exponential trend. So because of that, the concentration of cosmogenic nuclides is proportional to the time that the rock has spent in this production zone in the top 2 meters of the bedrock. So the concentration can be used to estimate bedrock exposure ages and also catchment average erosion rate. And that is the case because if a parcel of rock is eroding very fast, it's going to be exhumed to the surface very rapidly, and it's going to have very little time while sitting in these top few meters of the bedrock, so in this production zone. So by the time it reaches the surface, it's going to have a low concentration. So this would be, for example, here, the point in lighter orange. If erosion is very slow, the rock is going to be exhumed very slowly to the surface, and it's going to have a long time sitting in these top meters of the production zone. So by the time it reaches the surface, it's going to have a high concentration. So we can go to the catchment outlet and collect a bag of sand, and we assume that that bag of sand contains a representative mix of sand grains from different parts of the catchment that are eroding at different rates. So if we measure its concentration, what we are obtaining is the catchment average erosion rate. So because cosmogenic nuclide production and hence concentration decay exponentially with bedrock depth, landslides supply lower concentrations than superficial erosional processes, like this cartoon here shows. So continuous erosion, surface erosion, like here in the cartoon at the top, is generally assumed when inferring catchment average erosion rate. But landslides supply material from deeper in the bedrock, so it has lower concentrations, and they also do so in an episodic way. So some of the common assumptions for estimating erosion rates from cosmogenic nuclides are violated in landslide-prone areas, which raises the question of how representative can these estimates be. However, as some papers have recently highlighted, there's also a lot of potential for process tracing and for exploring landslide dynamics, but this is still very largely unexplored. So this makes quantifying the relationship between uplift and erosion rate challenging in landslide-prone areas. In most of tectonically active areas where this question is interesting are landslide-prone. This is further complicated by the scarcity of high-resolution uplift data to compare with the cosmogenic nuclide-derived erosion rate. So for the first part of the talk, I'm going to be focusing mostly on this point. And for the second part of the talk, I'm going to be touching more on the potential for understanding more about landslide dynamics. So in this first paper that I present today builds up from 3 previous papers in which we derived high-resolution slip rate data and examined the landscape response for normal faults in the southern Apennines and in Calabria. In this other paper in which we characterized the landslide activity in our study area. So because we had all this data from previous papers, we could address the following questions. How do catchment average erosion rates compare to fault uplift, nick point retreat, and incision rates? Can cosmogenic radionuclides provide reliable catchment average erosion rates in landslide-prone areas? And can we use cosmogenic nuclide-derived catchment average erosion rates to learn more about the long-term landslide activity? So normal faults are an excellent setting to address these questions because fault uplift rates may be relatively straightforward to constrain if there's some uplifted markers in the footwall. And also because they have a very well-studied pattern of landscape response to tectonics. So what I'm showing you here is a conceptual cartoon of half of a normal fault, from its tip, where fault flow rates are lower, to its center, where fault flow rates are higher. The rivers crossing this normal fault are going to try to keep pace with the base level lowering rate. So in this case, is that imposed by the footwall uplift. And in doing so, they are going to incise. And that incision is going to propagate upstream in the form of an upstream migrating nick point. And a nick point is a break and slope in the river long profile, as you can see here. As incision propagates upstream, the valley sides are going to steepen, often beyond their equilibrium angles, and landslides are going to start becoming the dominant erosional mechanism. Once the nick point has migrated all the way to the top, the catchment is adjusted to the full flow rate, so adjusted to tectonics, and we expect the catchment erosion rates to match the fault uplift rates. So based on all this, we can hypothesize that erosion rates vary with fault slip rate, but also with the degree of transient adjustment to those fault slip rates. And in this context, the degree of transient adjustment can be represented by how far upstream the nick point is, how much incision there is, or how much landslide activity there is. So we selected southern Italy to test this hypothesis, So here I'm showing you Google Earth image of Calabria, so the tip of the boot here looking towards Sicily, and that's Mount Etna. And I hope you've noticed already that the landscape here is dominated by normal faults. And these are the results of back-arc extension related to the Tyrrhenian subduction zone. But what makes these normal faults an ideal setting to test this hypothesis is this flat uplifted surface on the footwalls of the fault. So this is a relatively continuous marine terrace level that formed just before normal faulting started. And this is very useful for us for two reasons. First, because it represents a marker for fault throw that allow me to estimate profiles at high resolution of the fault uplift along the fault. And second, because it represents a pristine surface that is unadjusted to tectonics. So we can use this as a reference surface to estimate how adjusted to tectonics other parts of the catchment are. So we selected 15 catchments to measure beryllium-10 concentrations. Beryllium-10 is the most commonly used cosmogenic nuclide. And we wanted to learn the catchment average erosion rate. So I'm showing you here four representative of these 15 catchments. So what I'm showing here is the slope map. So green is lower slope and red is higher slope. So these catchments, as you will see later, are footwall catchments along the fault. But three of these catchments are the upper catchments above the nick point, so the unincised areas. These brown polygons are landslide maps. So we had mapped them in the previous paper, and this number represents landslide densities by area. And these long profiles are from the main channels draining each of these catchments. So what I hope you can see in these maps and also in this field image in Google Earth, in this field photo and Google Earth image, is that the catchments here are divided into two sectors. So we have an upper sector that is unincised, has low slopes and no landslides. So it still has not responded to tectonics at all. It's just being passively uplifted. And we have a lower sector, which is incised, has steep slopes and landslides, which is adjusted or adjusting to tectonics. And the boundary here is the nick point, which in this case it has not migrated all the way upstream because normal fault activity started only 1 million years ago. So you can see that our selected catchments are affected by different degrees of transient adjustment. So they have different proportions of this unadjusted flat surface at the top. And they also are affected by different fault slip rates. And that is because we collected our samples on catchments along an uplift gradient along a normal fault, like in the cartoon that I showed you earlier. So as I said, for each of these catchments, we have data from our previous papers on the footwall component of fault throw rate, which is the vertical component of the fault slip rates, and the one that these catchments are responding to. So here I'm showing you the fault throw rates on the x-axis. So they are generally between 0.2 and 0.8 millimeters a year. This point here at 0 millimeters a year is where I plotted the catchments that are above the nick point, so the ones that have not responded to tectonics yet. So they are affected by a virtual uplift rate of 0 yet. On the y-axis here, I'm showing you the maximum incision in each of these catchments and the height of the upper nick point. Because we know when incision and nick point retreat started 1 million years ago, we can convert this data into vertical propagation rates and incision rates. And in doing so, we can see that these rates are also in general between 0.2 to 0.8 millimeters a year. So we can see that the nick point vertical propagation and the incision are controlled by the fault activity and operate at very similar rates. So here I'm showing you the sample catchments in their positions along the normal faults where we've taken the samples. And our sample catchments are the ones in red, in black. And we obtain catchment average erosion rates of between 0.08 and 0.64 millimeters a year. I can also combine our data with some previously published estimates in the area. So here from Serre et al. And here from Olivetti et al. And in doing so, I noticed that all the samples collected above the nick point, so in these unadjusted and incised areas, are eroding at very consistent rates of about 0.1 millimeters a year. So I interpret this as the background erosion rate that operates in the area in absence of any tectonic forcing. So if we compare these beryllium-10 erosion rates here on the y-axis against the footwall component of fault throw rates in the x-axis, so the same I showed you earlier, we can see that there's a good correlation between both. And fixing the intercept at this 0.1 millimeters a year value, so this background erosion value, gives a best fit trend that suggests that the erosion is about half of the fault uplift, which reflects the fact that these catchments are not fully adjusted to tectonics yet. I should also say that some of these large error bars arise from, this large uncertainty arise from the uncertainties in the dating of this marine terrace level. So they are largely systematic. And also we know that some of this scatter is due to lithology. So for example, we know that granites in the area are about twice as weak as the gneisses, and they seem to be eroding about twice as fast for similar throw rate values. So we have confirmed the first part of this hypothesis. And also this seems like a very straightforward thing. It is actually the first time that this has been proven for normal faults with empirical data. And that's because other studies had troubles in determining reliable erosion rates due to landslide activity, and also had lower resolution of the fault throw rate data. So now we're going to examine the second part of the hypothesis, which is what is the role of this transient response of the incision and the landsliding in mediating this connection between fault activity and erosion. So here on these three graphs, I'm showing you on the x-axis the maximum incision depth. And remember that this is a metric for the degree of transient adjustment. Here on the left graph, in the y-axis, I'm showing you the beryllium chain erosion rate. And in this top right graph, the total volume of landslides in each of these catchments. And in the bottom y-axis, the total number of landslides in each of these catchments. So what I hope you can see is that as incision progresses, erosion rates increase, and they seem to be doing so because landslides get bigger and also more frequent. So what is remarkable about these results is that landslide activity does document the increase in landslide, is that beryllium chain erosion rate document the increase in landslide activity while still correlating with the fault throw rate. So we interpret that these catchment average cosmogenic nuclide erosion rates are providing reliable estimates. However, in this case and in most cases, we have just a geomorphic inventory with no time constraints. And hence we cannot compare directly the catchment erosion rates to the landslide erosion rates. But are there ways in which we can use this data to learn more about the long-term landslide activity? So yes, there are. And what we've done to address this question is to use this published model of cosmogenic nuclide and landslide dynamics. This model, this is by Brian Yanaitis and colleagues. And this model was designed to assess the probability that cosmogenic nuclide erosion rates capture the true long-term volumetric erosion rates in a study area. But it also produces other useful outputs. So because for our area, we think that our cosmogenic nuclide erosion rates are reliable, we are going to be using this model to estimate likely values of landslide recurrence intervals that make this possible. A landslide recurrence interval is essentially the time span in between two consecutive landslides in a parcel of rock. In this case, I'll be using a parcel of 1 kilometer squared. So it's a metric of how frequent landslides are. This is one elusive variable that's harder to obtain without repeated sets of aerial imagery, so knowing how frequent landslides are. And even when we do have this repeated set of aerial imagery, it's quite possible that a short time interval is not really representative of the long-term landslide frequencies. So this is why it's important to try to constrain the possible long-term values of these landslide recurrence intervals. So other inputs that the model uses are other parameters from landslide activity that are easier to constrain from geomorphic inventories. So things such as the minimum and maximum landslide areas, or the exponent in the power law decay in frequency from bigger to smaller landslide areas, or the volume area scaling relationship, all of which we have. It uses also a background erosion rate and a catchment area. So we are just going to be applying the model to try to get a general idea of what could be the median landslide recurrence interval value for our study area. So we are not trying to do this into any detail or modeling in real landscape, just getting a general idea. So we are going to be using all median values for the catchment area and for the other parameters. So here I'm showing you just the simplified model results. We've done this in a lot more detail in the paper, so I refer you to that. So here on the y-axis, I'm showing you the erosion rate. And on the x-axis, landslide recurrence interval values in years. The points are the modeled erosion rates, and this gray area represents the values of erosion rates where most of the observed beryllium chain erosion rates in our area fall. So this is actually the 25th to 75th percentile of the 38 values in our study area. So what this graph is showing is simply the fact that the erosion rates increase as landslide occurrence intervals get shorter. So a landslide occurrence interval of less than 5,000 years seems unlikely for our study area because it would produce much higher erosion rates than we have observed. I don't have time to show you, but we also can put in some constraints here based on the numbers of landslides. So based on those observations, we know that a landslide recurrence interval of more than 6,000 years seems unlikely because it would produce fewer landslides than we have observed. So putting all this together, we interpret that a median landslide recurrence interval of between 5,000 to 6,000 years seems more likely for our study area. So I've shown you a way in which we can learn more about the long-term landslide frequency using catchment average cosmogenic nuclide data. However, in reality, we know that landslide frequency depends on landslide size, with the smaller landslides being more frequent than bigger ones. So for the second part of the talk, I'm just very briefly going to present some results of my current project, LandFlux, in which we're using a different approach. So what we're doing here is measuring the the cosmogenic nuclide concentrations in recent landslide deposits, so here. And we are doing this to estimate landslide frequency more directly and on landslides of different sizes. So we addressed this question in New Zealand because it has very good decadal landslide inventories based on aerial imagery. So what we did here was sampling recent landslide deposits of different sizes. And we know all these landslides had occurred within the last 20 years or so. So for each of the landslides, we collected amalgamated samples of the landslide deposits, so of this type of deposit here, under the premise that these are representative of the bulk of the slate bedrock mass, in a similar way to catchment. So we also collected drone footage to build DMs of the landslide scars so that we can calculate the bulk production rate of the whole slate bedrock mass based on the distribution of excavation depths. So if we divide the measured beryllium-10 concentrations by this bulk production rate, what we obtain is an estimate for the exposure age. So basically, for how long that Hirsov was exposed to the cosmic rays before the landslide occurred. So here I'm plotting this in the y-axis against the landslide area on the x-axis. So you can see we find exposure ages of between 1,000 to 6,000 years, and that Hirsov that produce bigger landslides have been accumulating beryllium-10 for longer. So if we assume that in between two consecutive landslide events, the production profile of beryllium-10 is reset, which if you remember how fast beryllium-10 decays with depth is a reasonable assumption, we can consider these exposure ages as a proxy for the landslide recurrence interval. So essentially, what these exposure ages we're recording is the time span in between the landslide we've sampled and the previous landslide that had occurred in that same hill slope. So therefore, it makes a lot of sense that bigger landslides have a longer recurrence interval, or in other words, they are less frequent. And I should highlight that this is the first data set of this type, because previous papers that sampled with cosmogenic nuclides landslides, they did so with the goal of dating how long ago the landslide had occurred. So we know how long ago the landslides had occurred. We know they are very recent. And it's by knowing that and having a very good control on the landslide depth, the excavation depths in the scar, that we can, for the first time, infer information about the long-term landslide recurrence intervals. And what is exciting about this new data is that we can directly compare it to the published decadal inventories. So here I'm showing you a famous published decadal inventory from Hovius et al. Of the Southern Alps, which is based on 40 years of aerial imagery observations. So this is landslide frequency on the y-axis against landslide area in the x-axis. And this type of graphs simply represent the fact that smaller landslides are more frequent and bigger landslides are less frequent. But the slope of this decay in the frequency is quite important for landslide studies. So we can convert, our beryllium-10 based landslide recurrence interval into landslide frequency estimates, and we do so by calculating the inverse and scaling up to 1 kilometer per parcel. So if I plot my data together with the short-term inventory data, we can see the first thing is that it plots with a very similar slope to the shorter-term inventory, and that it produces some reasonable frequency estimate. And this is pretty remarkable because this inventory here is actually heavily beamed. So this is summarizing data from 7,000 landslides, and here we only have 12 landslides. So this is quite cool because now we have two sets of frequency area data, a short-term one and a long-term one. How long-term depends on its particular hill slope, but on average, this integrates over 2,000 to 4,000 years. So the comparison of these two data sets could suggest that there is an order of magnitude difference between the short-term and the long-term inventory. So we are currently investigating whether this is due to an increase in the landslide frequency towards the present, or whether this could reflect a spatial gradient in landslide activity, because most of our samples we collected very close to the alpine fault at lower elevations, while this inventory includes landslides all the way to the tree line. So to finish, I'd like to give you some brief take-home points. The first, that the erosion rates increase with fall slip rates, but also that the degree of landscape adjustment to those rates is very important. The second, that cosmogenic nuclides provide reliable catchment average erosion rates in landslide-prone areas under certain circumstances. In our case, we think that's true because the landslides are shallow and frequent. And the third point is that cosmogenic nuclides can be used to learn more about the long-term landslide activity on a time scale of hundreds to thousands of years that goes beyond any other current technique. And with that, I would like to thank you for your attention, and I'll be happy to take questions. Thank you very much.
Thank you very much, Duna, for a fantastic talk. It's really quite an impressive combination of fieldwork and dating and making use of previous published data, which I think speaks quite a lot to what Stuart Lane was talking about earlier about being able to share data and the fair data system. So I think we have a little bit of time for some questions now, I hope. And I have a question to start off with, if you can hear me, Duna.
Yeah, I can. Can you hear me?
Yes, I can hear you. So I was wondering if the Southern Apennines are a kind of a representative place, or do you think they're unique to other systems? How do you think they compare to other places in the world?
In terms of the normal faulting and the relationship with erosion, I think they are fairly representative of early rift phases, probably. But there's not so many, at least that I'm aware, places in the world that are at such an early rift phase for which we know so much about, and we are able to do this work because lots of other people have done lots of background work before. Yeah, there seems to be some similarities with some areas of the basin and range, for example. So I think in that sense of the evolution, they are pretty representative. And also there's a lot of work done in the Central Apennines too, that has a lot of similarities in terms of evolution. One thing that's quite cool about Calabria, I should say, is that in the Southern Apennines, is that in other parts of the Central Apennines, there's mostly carbonates outcropping, and it's harder to estimate catchment average erosion rates with cosmogenic nuclides for carbonates. So this is the value that we have in the Southern Apennines and in Calabria.
Yeah, so you've got lots to compare with. I have another question come in. So talking about your research in tectonic uplift, how might cosmogenic nuclides help understand erosion rates where there is tectonic fall? So for example, in the south of England, following post-glacial isostatic adjustment, so where the land is moving down.
Does it mean when the land is moving down, or when the rate of uplift and erosion are decaying? I would assume, yeah.
I'm not totally sure.
Yeah, if we have decreasing rate of tectonic activity, and we expect decreasing rate of erosion too, one thing that is starting to be quite promising is combining nuclides with different adjustment timescales, and they have different half-lives. So those can inform us about transient changes in erosion, whether that's increasing erosion or decaying erosion. So there's some cool work on that, mostly so far on glaciers, and to quantify deglaciation, complex deglaciation stories. But there's now a few published models that using different nuclides with different half-lives are able to constrain changes in erosion rates. So that's a cool avenue for future research.
Yeah, so you can be careful about which nuclide you use for which job.
Exactly.
So I've got another question. So from Fiona, she says, thank you for a great talk.
Thanks, Fiona.
Do you think that the difference in landslide frequency between the aerial inventory and cosmogenic datasets could be related to intervals of earthquake occurrence along the Alpine fault?
Yeah, that's a really good question. So we know that the last earthquake that ruptured across the Alpine fault was 300 years ago. And all these landslides have happened very recently. Also, the inventories in the last 40 years or so. And we also have catchment average erosion rate data that integrate over 300 years or so. So it's probably not related to earthquakes in this case, because there haven't been any recent earthquakes between the shorter term inventory and our longer term one. But we have two different types of data set that do point out. So the catchment average erosion rate data points out to a spatial gradient in erosion rates and landslide rate. So we know that actually the highest rates of uplift, well, there's different schools of thought, but it seems that the highest rates of uplift in the Southern Alps are actually not close to the fault, but a bit farther into the catchment. So therefore, where we sample, actually, we have lower erosion rates and lower landslide frequencies compared to if you integrate farther up in the catchment. We also have done some work dating on the same landslides with carbon-14, which, as I said, is like a shorter a cosmogenic nuclide that has a shorter half-life and can tell us things about transient changes in erosion, also erosional depth, actually. So we are now trying to investigate. So those actually also seem to point out that perhaps there's been an increase in erosion rates. But there's other things that could be complicating that signal, so we still have to do more work. And we're actually incorporating another nuclide in order to confirm that. So far, it seems that definitely there's a gradient in erosion rates in the Southern Alps with elevation. There could also have been a temporal change in erosion rates, but that we cannot tell yet. And in any case, it doesn't seem that earthquakes actually are playing such a big role for this data.
Great, Duna. Thank you so much for your answers. I think I'll go on to the next talk in the interest of time. I'm sure people have got other questions for you if they want to send them directly to you.
Or send me an email if you want later. I'm happy to answer questions to everyone.
Great. Thank you so much, Duna, and congratulations again on your work and your award. And good luck in your new position.
Thanks. Yeah. Thanks, Madeleine, and thanks everyone for listening.
Great.
Bye.
Thank you. Right.